Hey everyone, this is going to be a video about this Bertan Associates high voltage power supply that I just got from eBay. It's a model CRT 30, as the name kind of implies. It was used for cathode ray tube testing, and the 30 indicates that it can go up to 30 kV. This model actually has 3 outputs, as you can see here. This main anode output can go up to 30 kV at 2 milliamps. This focus output can go up to 8 kV at 1 milliamp, and the grid 2 output can go up to 1 kV at 1 milliamp. All of these outputs can be monitored, their voltage and their current. You can only monitor one at a time, so you can select which output you're monitoring for either of those with these switches here. I was able to get this for a very reasonable price. It looked like there were some similar models going for over $1,000 or a couple $1,000s. This one was only $250, and the listing said that it was in working order, so I went ahead and bought it. And when I got it, the power cable that was hooked up was some very odd connection that wasn't going to plug into my wall. So I had to go ahead and replace that, but plugging it in and turning it on, it seems to work. The one thing that it didn't include, though, was any of the high voltage output connectors or cables. So in today's video, I'll walk through the process of how I 3D printed some high voltage connectors for this. So the first thing I had to determine was what this thread was, so that I could 3D print a mating thread. And I was able to use a feeler gauge, this one here, to determine that it was 16 threads per inch, and then measuring the outer diameter gave me 3/4 of an inch, so I knew that this was a 3/4 16 thread. So once I knew what thread diameter and pitch it was, I was able to go into Autodesk Inventor and model a mating thread for this, and I'll throw up on the screen a quick capture of how I did that. But basically I went to McMaster and found a 3/4 16 bolt that would represent this male thread here, And I took that bolt 3D model from McMaster and put that in Inventor. So then in Inventor, I was able to directly edit the surface of the threads to increase it by 5 thousandths, 10, 15 thousandths, whatever I wanted. And I could use that as a blank to make a female thread. So I went ahead and printed some test samples of this thread, and I started with 15 thousandths clearance and found that that was a little too loose. You know, it would lock in there, but it's pretty sloppy for a thread. So then I tried just 10 thousandths clearance, and that similarly would have worked well, but it was still a little sloppy. And so I decided to try just 5 thousandths clearance to see if that would be too tight. And it actually turned out that fit really well. There's still plenty of clearance to where it can spin freely, but there's not much noticeable wobble. So after I determined the outer thread, it was just a matter of taking measurements of the inner diameter and the depth of this cavity, and modeling that also in Inventor, and printing something like this that can insert into that cavity. Now, one of the difficult parts was figuring out what diameter that male pin in there was, and it's very difficult to see down there and get a measurement, but I initially estimated that it might be a 1mm pin, so I ordered some of these D-sub style female connectors because the nominal D-sub male pin diameter is 1mm. But unfortunately, that was a little too small diameter, and it wouldn't push on there without deforming the contact. So then I assumed, okay, maybe it's a 1.5mm male pin in there, and I was able to get some of these Deutsch style contacts where the male pins are 1.5mm in diameter, and so the female pins would mate well to a 1.5mm pin. And thankfully that was a great fit, nice and snug. So then I just designed the internals of this insert, which you're not going to be able to see here, but I can again show a cross-section in Inventor. I had to design this female socket to lock in place inside this so that when it gets pushed in there, it can stay in, and also when it's getting pulled back out, it'll stay in place. And thankfully that was all easily 3D printable in place, all in one piece. So you can see this initial design just has a flat back here, and I figured the high voltage cable will insert there and will have been soldered to this socket. And then my first design for the outer threads was something like this that has a pass-through for the high voltage cable and just a flat back in there to push up against this surface and hold it in place. And while that certainly would have worked, I didn't want to have to unscrew this connector here and then probably pull on the cable in order to get this out, because it's a fairly tight fit and this doesn't leave me much room to grab onto. So I wanted to figure out a way to have this thread become captive on this centerpiece so that when I pull the thread out, it pulls the centerpiece out and isn't relying on the cable to yank the connector out. So all I did was add some fingers on the back here and increase the diameter of the through hole in this thread, and I was able to get, as you saw earlier, a 3D printable connector that clips together and spins pretty freely, but stays captive so that when it's inserted and threads on, it draws it in, and when I want to take it out, it pulls it out. Alright, so you can see now with the cover off that it's pretty dirty inside, but still powers on, but it's probably worth cleaning. So it looks like we've got power coming in here, going to this transformer. It likely steps the voltage down. You see that going into this filter capacitor here, and then that's feeding, looks like, the rest of the electronics. So we have 3 modules here that correspond to the 30 kV, 8 kV, and 1 kV outputs. So all those outputs are completely independent with their own modules. And it looks like we've got our 3.5 digit 7-segment displays here. And then we have some sort of control board, and the wires are all routed to the switches and dials on the front. So this is the brains of the operation, and looks like here we have some power transistors and a set of resistors here that are cooled by this fan. It's relatively simple circuitry for controlling all 3 supplies. And one thing I'll bring you closer to see is that this board was all hand layout. There's no CAD involved as far as I can tell. Let's go ahead and get a closer look. So you can see the hand-drawn traces here. It's pretty interesting. You don't see that very often, and I think that probably dates this supply to the late 70s or early 80s. CAD software, though it was produced or invented maybe in the 60s, didn't really come into common use until throughout the 80s. And so, you know, in the early mid 80s, you had companies popping up like Cadence, Altium, OrCAD, Mentor Graphics, and designers slowly adopted the CAD tools rather than doing hand layouts. Kind of through the late 80s and then into the 90s, that was kind of the new standard. So this board was likely designed in the late 70s, possibly right around 1980. But I was able to find very little information on this model of power supply, really just a few ads in some scanned documents, and I'll throw those up on the screen. So that's where I got the specs for the outputs. Other than that, it doesn't really tell us much about when it was made. So I was trying to find a date somewhere on either the PCBs or just stamped somewhere, and I was finally able to find on the back side of this transformer. You can see it's also a Bertan Associates made transformer, that there is a date there. So it looks like 12/11/81. So early 80s is when this was built. Possibly was designed a few years before that, but that kind of confirms what around the range that we were suspecting. Here's a little bit of a closer up on these high voltage modules. You can see the 30 kV one is totally encased in a metal casing. The 8 kV is just potted in a kind of some sort of silicon material maybe. It's compliant, but it's, you know, fairly stiff. And then the 1 kV supply, you can see, is still totally exposed. You've got what looks like maybe a flyback type transformer here, and then some power switches. So that isn't high enough voltage where it needs to be potted. You're not going to have significant corona discharge at only 1 kV. Whereas for these other two, certainly 30 kV, that could be an issue. So you want to have that potted so nothing flashes over or discharges. So I'm hoping to be able to use this power supply to test and help design some high voltage relays for some other work. I'm thinking something similar to a Ross relay, if you're familiar with that. I'll go ahead and throw a picture up on the screen. But something that's good for, you know, a few tens of kV and pretty substantial current. They're ideal for safety dump circuits because all the contacts are fully exposed and you can see if it has mechanically acted or not. And so if you have a fail-safe circuit that's supposed to dump a big capacitor bank, and you hit the e-stop or whatever condition happens that it's supposed to dump, you can see and usually hear if it does, and if for some reason the contacts are welded together or something is wrong, you can observe that as well. So they're really nice for safety applications in dumping large capacitor banks. And I'm hoping to be able to design a 3D printed version that uses some sort of off-the-shelf relay and maybe some simple contacts that can be purchased off the shelf as well. So I'll be thinking about that over the next week or so, and hopefully I'll be able to use this to test it up to 30 kV. Thanks for watching.